Hello everyone, and welcome. Today, we are beginning an exciting journey into the heart of modern technology. Our focus for this session is the mathematical foundations of AI. While AI often feels like magic, it is actually built on a very solid bedrock of mathematical principles. To understand how AI works, we need to look at four core pillars. First, linear algebra acts as the language of data, allowing us to represent information in high-dimensional spaces. Next is calculus, which is the engine behind learning. It provides the optimization tools needed for models to improve. We also rely on probability to quantify uncertainty and statistics to identify meaningful patterns within data. As you can see from the visualization here, these fields don't exist in isolation. They intersect and support one another to create the complex architectures we see in neural networks and machine learning models. In this table, we can see the direct applications. For instance, linear algebra is fundamental for creating word embeddings, while calculus is what makes backpropagation possible. Throughout today's session, we will break these down step by step, starting with the basics of vectors and tensors. Let's dive in. Building on the introduction we just covered, let's dive into the fundamental building blocks of AI mathematics, vectors and tensors. We categorize data by its rank or dimensionality. A scalar is simply a single numeric value, like the temperature in this room. A vector is an ordered list of numbers, giving it direction and magnitude in space. As we move to grids of numbers, we call those matrices. When we generalize these concepts to any number of dimensions, we use the term tensor. As you can see in the notation here, a tensor can represent highly complex, multidimensional data structures. Take a look at this chart. It illustrates how the data dimensionality scales. In modern neural networks, we often work with tensors of 4, 5, or even more dimensions to process batches of complex information simultaneously. A perfect real-world application is a digital image. We don't just see it as a flat picture. The computer sees it as a 3D tensor. It has height and width, but also a third dimension for color channels red, green, and blue. This structure allows the AI to see and process every detail of the image. Building on our understanding of vectors and tensors, we now need to look at how these structures interact. At the heart of nearly every AI operation is matrix multiplication and the transformations it enables. First, let's focus on the most basic building block, the dot product. This operation essentially measures vector similarity. In AI, this formula is a fundamental building block. It's how we determine how closely an input, like the pixels of an image we just discussed, matches a learned pattern. When we scale up to full matrices, we must follow strict rules. As you can see here, for a multiplication to be valid, the inner dimensions must match, meaning the number of columns in our first matrix must equal the rows in the second. The resulting matrix, C, takes its size from the outer dimensions. Managing the computational complexity of these operations is why high-performance GPUs are so critical for modern AI. But matrix multiplication isn't just abstract arithmetic. It represents a geometric transformation. It allows us to map input data into a new space through effects like rotation, scaling, and shearing. This is exactly how a neural network learns. Each layer's weights are a matrix that transforms the data, extracting increasingly complex features as it passes through. Now, let's get ready to see these transformations in action in our upcoming lab. Now that we're in the lab, let's apply what we just covered about matrix multiplication to see how it physically transforms space. On the left, you have a 2D grid, and on the right, the 2x2 matrix that controls its shape. Start by looking at the current values. When the matrix has 1s on the diagonal and 0s elsewhere, it's the identity matrix. Move the sliders for R and D, and observe how the grid stretches or shrinks. This is scaling in action. Now, let's try some specific movements. Click the Rotate 90 deg preset. See how the entire coordinate system pivots? Notice how the values in the matrix changed to achieve this specific rotation. Try playing with the B and C sliders. These create shear transformations. tilting the grid. Observe how the area of the grid cells might change, even if the lines remain parallel. For a final challenge, try to set the sliders so the entire 2D grid collapses into a single line or a point. This happens when the matrix is non-invertible. Witnessing this collapse is crucial for understanding how data dimensions are reduced in AI. Take a moment to explore different combinations. When you're ready to test your intuition on these transformations, we'll move on to the knowledge check. Building on the foundations of linear algebra we just established, we're now moving into the second major pillar of AI mathematics, calculus. Specifically, we'll focus on the power of the derivative. The derivative is a fundamental concept that describes how a function changes at a specific point. In AI, this allows us to understand the sensitivity of our models to small changes in their inputs. Mathematically, we define it using this limit formula. It represents the slope between 2 points as the distance between them, shrinks to 0, giving us the instantaneous rate of change. To make this more intuitive, let's look at the visual representation here. By visualizing the slope of the tangent line, we can see exactly where the function is increasing or decreasing. This is vital for minimizing error. We follow the derivative to find the lowest point of an error function. Next, we'll look at the specific rules for calculating these slopes, like the power and product rules. Building on the basic rules we just covered, let's dive into the core engine of deep learning, the chain rule and partial derivatives. In a neural network, functions are stacked within one another. The chain rule is our tool for calculating how the final loss changes as we move backward through these nested layers. Take a look at this computational graph. It represents how variables interact. To find the influence of a weight at the start of the graph on the final result, we multiply the derivatives along the connecting path. This brings us to partial derivatives. This formula shows the derivative of the loss L with respect to a specific weight W. It tells us exactly how changing just that one weight will affect our total error, keeping everything else constant. By organizing these partial derivatives into a gradient vector, we determine the direction of steepest ascent. This logic is the foundation of backpropagation, which allows the model to learn from its mistakes. Next, we'll see this in action with a gradient descent simulation. We just explored the chain rule and partial derivatives. Now let's see how they actually drive the optimization process. This 3D map represents our loss surface, where the height at any point indicates the error of our model. Go ahead and click anywhere on the surface to set your starting point. Then, hit the step button to see how the gradient tells the ball which way is down toward the local minimum. Now, look at the learning rate slider. This controls the size of each step we take. Try setting it to a small value and clicking step several times to observe a steady, controlled descent. Let's experiment with what happens when we're too aggressive. Move the slider to a high learning rate and observe the path. Notice how the ball might bounce back and forth across the valley, or even move further away from the bottom. This is the overshooting effect. Take some time to find the sweet spot where the ball reaches the lowest point as efficiently as possible. Finding this balance is a critical part of the optimization process we'll revisit at the end of this session. Building on how mathematical foundations impact model performance, as we just discussed, we must now address the inherent uncertainty found in real-world data. This brings us to probability distributions and random variables. In AI, we distinguish between discrete variables, like a yes or no classification, and continuous variables, which can take any value within a range. Depending on the data, we use specific distributions, like Bernoulli for binary outcomes, or multinomial distributions for multi-class problems. Take a look at this bell-shaped curve. This is the Gaussian, or normal distribution. It is perhaps the most important concept in statistics for AI, often used to represent the distribution of errors or to initialize the weights in a neural network. We use the probability density function, or PDF, to describe the likelihood of a continuous random variable taking on a specific value. Understanding why the normal distribution is so ubiquitous will help us as we move into more complex statistical inference. Next, we'll explore how these probabilities interact when we look at Bayes' theorem. Building on our discussion of random variables, We now arrive at one of the most influential concepts in artificial intelligence, Bayes' theorem. This theorem provides a rigorous mathematical framework for updating our beliefs based on new evidence. Take a look at the formula here. It defines the conditional probability of A given B. In the context of AI, we often think of A as our hypothesis and B as the observed data. This equation tells us exactly how to adjust our confidence in a hypothesis after seeing that data. To understand this, we break it into parts. We start with the prior. This is our initial degree of belief before we've seen any evidence at all. Then we consider the likelihood, which describes how well our hypothesis explains the evidence we just observed. The result is the posterior probability. This is our updated belief. It's the core of how machines learn from experience. They are essentially performing this calculation over and over to refine their understanding of the world. In practice, you'll encounter this in naive Bayes classifiers, which are often used for text filtering, and in Bayesian networks that handle complex reasoning under uncertainty. Next, we'll see how these probabilistic foundations lead us into the world of descriptive and inferential statistics. Building on the probabilistic foundations we just covered, we now move into statistics, which is the practical art of making sense of data. We can divide this field into two primary branches: descriptive and inferential statistics. First, descriptive statistics focus on summarizing and organizing data so we can understand its basic characteristics at a glance. We rely on metrics like mean, variance, and standard deviation to describe the center and spread of our data points. It is also here that we must carefully distinguish between correlation, how two variables move together, and causation. However, in AI, we often need to go further. Inferential statistics allow us to take samples of data and make generalizations or inferences about a much larger population. One of the most critical tools here is maximum likelihood estimation, or MLE. This formula helps us find the parameter values that maximize the likelihood of making the observations we have, which is essentially how many machine learning models learn. When we apply these concepts to things like linear regression, we use p-values and significance testing to evaluate if the relationships we see are real or just a result of random noise. This ensures our AI models are grounded in statistical truth. Now that we've explored probability and statistics, we have all the pieces of the puzzle. Let's see how these mathematical pillars actually fit together to train an AI model. It all starts with step 1. Defining our parameters. As we discussed earlier when we covered linear algebra, we represent the data and model weights using vectors and tensors. This is the structural foundation of the entire system. Next, in step 2, we apply the statistics and probability concepts we just finished. We define a loss function to quantify the model's performance, measuring how far off our predictions are from reality. Step 3 brings in the calculus we studied earlier. We compute gradients using the chain rule to perform sensitivity analysis, determining how each weight contributes to the overall error. Finally, in step 4, we use gradient descent to update those weights. This is an iterative optimization process, looping back until the model reaches its peak performance. Take a look at this training loop. It represents the beautiful synergy between these math disciplines. Before we move to our final summary, I'd like to hear your thoughts on which of these steps you think is the most difficult to get right in practice. To wrap up our journey through the mathematical foundations of AI, let's take a moment to look at how everything we've discussed today fits together into a cohesive roadmap. We've navigated from the structural foundations of matrices and linear maps, through the optimization power of gradients, to the statistical nature of probability distributions. These aren't just isolated topics. They are the combined tools you'll use every day in AI. As we move forward, remember that rigor is your best friend. In AI research, precision is the foundation of high-impact results. Moving beyond black box thinking to understand the underlying mechanics is what sets a great engineer apart. To continue your development, I highly recommend exploring advanced calculus and information theory. These resources will help you bridge the gap between current intuition and the complex architectures you'll encounter in the field. The final takeaway is simple. Never stop bridging the gap between your intuition and the formal math. That balance is where innovation happens. The journey to mastering AI engineering begins with these core concepts. You've done excellent work today, staying engaged with these challenging topics. Keep practicing, stay curious, and I wish you the best of luck with your future projects. Thank you for being part of this class.